Now that we know that we can add multiple explanatory variables to our model, a natural question that arises is how do we decide whether adding more variables has improved the model or not? This is actually where we are going to spend a lot of time later in this course, but I want to take the first cut at it this week. The first cut is simply to use the adjusted R-squared. Now, before we jump into what adjusted R-squared is, I want to start with a discussion on why we do not want to use the standard R-squared, also called multiple R-squared, for model comparison. First, recall that R-squared is a percent of variation in Y that's explained by the x's. Recall that regression uses the correlation between variables to minimize the sum of the squared residuals, and that this sum of squared residuals is also in the numerator of the R-squared formula. Then finally, recall that there is almost always some correlation between any two variables, even when we randomly generate one. So you are very unlikely to see a correlation coefficient of exactly 0 between a dependent variable and one of the explanatory variable. Well, that means that R-squared will increase whenever we add a new variable to the model. No matter what that variable is, as long as there is some variation in it, it will increase the R-squared in a linear regression. So adding a variable will never decrease the R-squared, because in the worst case, the slope coefficient for this new variable will be 0. Here is an explanation of why adding a variable can only improve predictions in our sample. You see that model 1 has x1 and x2 as explanatory variables. You see that model 2 also has x1 and x2, but it also has x3. Now, suppose that x3 is useless to predict y. Then we can just set beta 3 to be 0, and we have exactly the same equation as model 1. We say that the model 1 is nested in model 2. So model 2 is capable to do at least as good as model 1. The lowest R-squared that model 2 can get is at least the R-squared of model 1. And that is when the estimated beta 1 in model 2 is the same as model 1, the estimated beta 2 in model 2 is the same as model 1, and beta 3 is 0. Then we have the same model. Now, if x3 is at least a bit informative and can help predict y better than just with x1 and x2, then beta 3 will not be 0, and our R-squared will improve when we add it. If we look at model 3, it also has x3, but it doesn't have x2, so it's not the same. In that case, there is no configuration of model 3 where it would do exactly the same as model 1. In that case, we say that model 3 does not nest model 1. So when a model nests another, the R-squared can only be as good or better. So using the R-squared to compare two models when one nests another, it's useless because it will always tell us to add more variables. So what should we use instead of using the standard R-squared? Well, we are going to use the adjusted R-squared for our model comparisons. It's similar in calculation to R-squared, but in addition to the standard equation, it also has a penalty term for additional parameters. I have put the formula here, but you don't need to learn it. It's just for your own information. What we can think of that penalty term is looking if R-squared increases by an amount that is larger than what we would expect if we added simply a random number. So it's penalizing R-squared for adding additional parameters and variables that are not performing well. It's forcing the model to do even better than what we would expect from a randomly generated number. As for the standard R-squared, higher is better in this case too. So if we are comparing two models, we can look at their adjusted R-squared and pick the one with the highest. This is particularly useful when we have one model that nests another model. Now, there are some cons to using adjusted R-squared. First, it does not have that elegant interpretation of the percent of variation explained. So we shouldn't look at that number and try to interpret it that way. It doesn't really have any intuitive definition at all, actually. It's just a penalized r squared. Also, it's only going to evaluate within the sample fit, which means that it sometimes misleads us to, if the correlation between the variable that we added in our outcome of interest just happened to be strong enough in our sample, but maybe it doesn't reflect the correlation in the overall population. We will talk more about this next week and ways that we might be able to resolve that concern. There are challenges and problems with the adjusted r squared, but it is usually a pretty helpful heuristic. Next week, we'll talk about other ways we can use to compare models and determine which variables we might want to include or exclude from our regression equation. Finally, let's look at typical regression results from a statistical software. We can see here that the software provides the standard r squared, here called the multiple r squared, and it is interpreted as the share of explained variation in our dependent variable. We have also next to it the adjusted r squared, which is the model performance given the number of variables.